Are you able to see the screen? Can anyone confirm?
Yes, sir.
Okay, all right. So here and there, bits and pieces are left in module 2 as well as module 3. Okay, so let me just you know tell the topics that I'm going to cover in today's class. All right. So Darlington AC circuit, which is part of module 3, Miller capacitance, which is part of module 2. Okay, and relation between H model of CE, CC, and CB. M2, that is module 2, and cascade and cascode connection, that is M3. Okay, fine. So first let me take up the first one, that is relation between H model of CE, CC, and CB. Okay, fine. Relationship in the sense, if you look at common emitter configuration, what is the counterpart of H parameters of common emitter configuration in common base configuration? Okay, so it's something like this. If you have the details of, let us say, H parameters of common base configuration, all right, so these are CB parameters, right? So these are CB parameters. Let's say you have been given with HIB, HFB, HOB, and HRB. How will you be able to find the common emitter configuration? Okay, so there is a proof, but that proof is, it's very tedious. Okay, and it will not be asked in exam also. But only the down part of this discussion is that you need to by heart these equations. Okay, so only over here, okay, you will encounter, which I normally don't like. You have to by heart whether you like it or not. Okay, if let's say you are a person who doesn't want to by heart, probably in external, if at all you get any question based on this, probably you can skip this one and you can attempt the other one, because very less chances that this particular topic will appear in both the questions. Okay, but logically you can remember. All right, so similarly, you also have conversion equations for common collector configuration. Let's say, for example, you have the parameters of CB given. Okay, CB given. So with the CB parameters, you can find out the common collector parameters, right? See, HIC is approximately equal to HIB divided by 1 plus HFB, right? Now, what I want you to tell you is that if you look at closely, common emitter configuration and common collector configuration, the equations are look-alike, right? The equations are look-alike. For example, conversion from common base parameters to common emitter parameter. If you look over here, what is HIE here? It is HIB divided by 1 plus HFB. And if you look at common collector configuration, in place of HIE, you have HIC. Okay, and the formula remains the same, right? HIB divided by 1 plus HFB. So this common emitter and common collector, it is kind of similar. Okay, kind of similar. Only the difference what you can find is somewhere here. Okay, somewhere here. HRE is, this HIB, HOB divided by 1 plus HFB minus HRB. On the other hand, HRC is approximately equal to 1. All right. And if you look at HOE expression, it is matching with HOC expression. HIE is matching with HIC. Okay. Only HRE is differing. Okay. And HFC also, to some extent, it follows the same expression. Okay. HFB divided by 1 plus HFB. Okay. And I'm very sure that there is some print mistake in Boyle state, because HFE, they have taken it as beta, and HFC, that also they have taken it as beta. Hence, in the numerator, you have to have the same terminology, Okay, so let me just correct this. It should be minus HFP. Minus HFP. All right. So this is the similarity between the common collector and common emitter configuration. Okay, and common base configuration. Okay, let's say you are being given with C parameters. Okay, so with the C parameters, how will you find the CB parameters? How will you find CB parameters? So HIB is, again, if you look at this particular equation, okay, HIB. So you have been given with C, right? So HIB is equal to the same equation if you see. HIE divided by 1 plus HFE. Okay, so I'm not explaining anything over here. I'm just trying to, help you to figure out the things, okay, the similarities. Okay, it takes some time to memorize these equations. Okay, no worries. If you have any trouble in memorizing this equation, you can skip off and you can attempt the different question in external examination. If you can memorize, this is the trick what you can follow. Okay, all right, fine. So that's about your relation between H model of CE, CC, and CB. Okay, so this it's rarely they last. Okay, less likely to come. Less likely to come, however, which is required for lab. Lab, it is required. Okay, but in lab, what I will do, normally I'm a guy who doesn't promote students to buy at the things. So in lab, what I will do, even in externals, I will try to give you these conversion equations. Okay, all you need to do is the experimental setup is your headache. Okay, but you don't have to memorize the formula. I will provide you, okay, as a appendix. Okay, as an appendix, I can provide you in the lab. Fine. So that's about the first topic of the day, which is relation between H model of CE, CC, and CB. Okay. Next, let me take up Darlington circuit AC analysis. Okay. See, I had given you the AC equivalent circuit question in internals, right? You could do it because AC analysis doesn't differ much with the conventional single stage emitter follower circuit, right? The H model or RE model remains the same for Darlington emitter follower circuit or a conventional single transistor emitter follower circuit. Okay, no problem. I'll just quickly tell you how exactly you determine the performance parameters. Okay, so figure A represents the circuit diagram. Okay, as you can see, this is based on the basis of emitter bias circuit, right? You have resistor RB and you have biasing resistor RA. Okay, one noticeable difference is that it doesn't have a collector resistor. Okay, this is what is required for an emitter follower circuit. Okay, there are two transistors having individual gains as beta 1 and beta 2. So for our analysis, what we will do is we will consider these two transistors as a single transistor with an overall gain as beta D. Okay, and that overall gain beta D, we can define it as beta 1 into beta 2, which is approximately beta square, provided beta 1 and beta 2 are very close to each other or they are identical to each other. So the overall current gain is beta square. Okay, and the other important aspect of emitter follower circuit is that the output is absorbed from emitter terminal. Okay, so the output is not absorbed from collector terminal, like your unlike your amplifier circuit. All right, fine. So that's your circuit diagram, and figure B, talks about the equivalent circuit. Okay, since there are two transistors, beta 1 and beta 2, okay, so each transistor will have beta RE or HIE, right? So what we have done over here is that since we are replacing the two transistor with a single transistor, Hence, we have taken the overall input impedance of the Darlington pair as Ri. So, Ri is overall input impedance of Darlington pair. All right. So, on the input side, we have represented Ri, which represents the overall input impedance of Darlington pair. And on the output side, this collector current IC flows, right? So this is your collector current IC. This is your base current IB. Okay. And this is your emitter current IE. Okay. So IC is given as beta times IB. Since we are talking about a Darlington transistor, it becomes beta D times IB. All right. So that's your IC. And on the emitter side, you have an ungrounded emitter resistor. I mean, not ungrounded, non-short circuited emitter resistor. That's the reason, RE exists. Okay, fine. And the capacitor, okay, C naught, you're going to short circuit. Okay, and the output voltage is observed right across the emitter resistor. All right. And on the input side, you have conventional input current IA. Okay, and some current IX will flow through the biasing resistor, and the remaining current will flow in as the base current IB. All right, so this is your equivalent circuit of Darlington emitter follower. All right, fine. Now let us look at the performance parameters. First, let us find out Zi. Okay, pretty simple. Okay, just like your emitter follower, you can find out Zi as well. So what we will do is, let us define, an assisting impedance ZB. Okay, so ZB we have marked very close to the base terminal. Okay, and we will shift Vi, okay, on the base terminal. Okay, next to base terminal, let us shift the input voltage. Okay, so you can write the input voltage Vi as, you can apply KVL. So that's IB into Ri plus IE into RE. But IE is basically 1 plus beta D times IB, right? So beta D you need to bring in. Okay, it's not just beta, it is beta D. And therefore, you would get Vi as IB times Ri plus IE. So I'm going to replace IE with this. That's 1 plus beta D into RE, right? So that's your Vi. Or you take out the ratio Vi by IB, voltage by current ratio is impedance. And that impedance ratio, you will get it as Ri plus 1 plus beta D times RE. Okay. So that's your ZB. Therefore, input impedance Zi is equal to the base resistance RB, which is nothing but the biasing resistor, in parallel with ZB, right? So that's your overall input impedance. Okay, and I can here itself propose the approximation. So ZB can be approximately written as Ri plus beta D times Re. Okay, approximately you can write it down, no problems. Okay, fine. And this beta D is very large. Okay, let me write it in words. Is very large, and if it is found that beta D into Re is very much greater than Rn, your ZB going to be simply beta D times Re. Beta D times Re. Provided the product beta D into Re is very much greater than R. Okay, so that's your input impedance. Okay, so next let me take up the current gain AI. Current gain, yeah. Okay, just excuse me for a couple of minutes. Okay, sharp 2 minutes. Yeah, thank you. So current gain AI is equal to output current to the input current. Okay. Now, in order to find a current gain, okay, over here, the current gain analysis is not that straightforward. That's because there are two transistors involved. Okay, even though we have taken the overall current gain as beta D, okay, it makes sense to provide the realistic picture of current gain. Okay, that's the reason, I'm following this type of derivation. Okay, so what I will do, I naught by II, let me write it in this manner. So I naught divided by, don't worry, what is it, into, don't worry, what is the numerator, write on II. Okay, and then what you do is multiply and divide by IB. Okay, so mathematically, no harm done, right? Because IB is gonna cancel out with this IB. So you are left with I naught by II. Now, by doing so, what we get is a proper relationship between the two currents. Okay, because on the input side, you have current II as well as you have current IB, and on the output side you have current I naught. So you will be able to relate all these currents together. Okay, now we know that, okay, but we know that I naught is equal to IE. Okay, let's say equation 2, and let's say this is equation 1. All right, so therefore we can write current gain AI as I naught, which is IE by IB, all right, into IB by IA. Okay, and we shall take this as equation 3. Okay, also we know that IE is equal to 1 plus beta D times IB. Okay, or approximately you can write it as beta D times IB. Okay, so what we will do is that implies the current gain beta D is IE divided by IB, and we shall take this as equation 4. So IE by IB is beta D. So you can sub equation 4 in equation 3, so that you will get current gain AI as beta D into the input current ratio IB by IA. Okay, so let's take this as equation 5. Okay, now IB by II relation can be obtained from the input circuit. Okay, that's because both IB and II are found on the input circuit. All right, so what we will do is let us apply KCL. Okay, let us apply KCL at let's say node B dash. Okay, B dash and B is one and the same. I don't want to erase B, so I'll just take B dash. So if I apply KCL at B dash, what do we get? Summation of incoming current is equal to outgoing current. So II is equal to IX plus IB. We shall write it. So at node B dash, apply KCL. So what do we get? We get II is equal to IX plus IB. Okay, or II is equal to IB plus IX. So IX is nothing but current through the biasing resistor RB. So what is IX? IX is nothing but voltage divided by resistance. So I can write IX as voltage divided by resistance, that is RB. Okay, fine. Okay, or okay, so yeah, then also from the circuit, okay, also from the circuit, you can write II as, if you see, okay, also you can write II is equal to the total voltage, okay, that is VI plus IB into RB, okay, IB into RB divided by the resistance RB, okay. So from the circuit, we have VI is equal to IB into ZB, okay, or you can write II is equal to, okay, VI plus IB into RB divided by RB. Okay, this is capital RB. Or you can substitute here. So this becomes IB ZB plus IB RB divided by RB. Okay. Or II is equal to, you can take out IB common, IB times ZB plus RB, okay, divided by RB, or take out the ratio IB by II. Okay, so IB by II ratio. So I will get RB divided by ZB plus RB. Okay, so let's take this as equation 6. Okay, so substitute equation 6 in equation 5. Okay, so IB by II ratio we know, so we can substitute equation 6 in equation 5. So that will give us current gain AI as beta D into this resistance ratio. Okay, that's RB divided by ZB plus RB. So that's a current gain. Okay, that's a current gain. Okay, so ideal current gain is beta D, but from your actual circuit, you would get the actual current gain as beta D into some limiting factor, and that limiting factor is nothing but RB divided by ZB plus RB. Okay, so that's your current gain. Third one, voltage gain. Voltage gain is also very simple. So to find voltage gain, what I will do is I will recreate the circuit. Okay, this is your base terminal. This is your RI, okay, and then you have your RE. Okay. So this is your ground terminal. Okay, let us mark VI here, minus plus. Okay, this is your RE. Okay, through RI, current IB flows, and through RE, current IE flows. So therefore, okay, and this itself is V naught basically. Okay, voltage which is appearing across RE is our V naught. Okay, let me show you in the main circuit. See, voltage across RE is V naught. So same thing I have shown in the equivalent circuit as well. Okay, so therefore you can write V naught is equal to current into resistance, that is IE into RE, or IE is 1 plus beta D times IB into RE. Okay, so let's say equation 1. Then on the input side, you can apply VI is equal to, okay, you can apply KVL. So what do you get? IB into RI, okay, plus IA into RE, which is equal to IB into RI plus IE, let's write it as 1 plus beta D times IB into RE. Or you can um, even use voltage gain expression, because you have V naught and you have Vi. What is voltage gain? Voltage gain is ratio of output voltage to input voltage. So therefore AV is equal to V naught. So V naught is 1 plus beta D into IB into RE, okay, divided by Vi, which is IB is common, all right. So let me take IB outside the bracket. So within the parenthesis, I'm left with Ri plus 1 plus beta D times capital Re. Okay, so IB gets cancelled. So voltage gain, you will get it as Re divided by Ri plus 1 plus beta D times Re. Okay, so this is the exact expression. Approximate expression, just to show that voltage gain is closer to unity for an emitter follower circuit. So approximation you can do. Okay, so numerator remains Re. Okay, in the denominator you can write Ri plus 1 plus beta D, we shall take it as beta D, okay, into Re. All right. Okay, so yeah, here also, right? This is also beta D into Re. I'm so sorry. This is 1 plus beta D into Re. I think I missed out this term. Okay, so 1 plus beta D, we can write it as, approximately beta D. So you have beta D into Re in the numerator. Similarly, in the denominator, you have beta D into Re. Okay, or approximately, you can also take the denominator as beta D into Re, as beta D into Re is very much greater in comparison with Ri. So basically, these two will get cancelled out with each other. Hence, you will get voltage gain approximately equal to 1. Okay, that means to say, for a Darlington emitter follower circuit, output is equal to input, and phase shift, okay, between V naught and Vi is equal to 0 degree. So it doesn't amplify the signal, and it doesn't even change the phase value of the signal. Okay, it simply transfers a signal from one port to the other without any amplification. Okay, fine. So that's your voltage gain. Okay, the third one is the output impedance. Output impedance. So this output impedance is pretty tricky. Okay, so for output impedance, let us do it on the basis of Thevenin's theorem. All right. So what I will do for the output impedance, you can apply Thevenin's theorem. Okay, that is short circuit Vi. That implies Vi is equal to 0. Okay, and you can actually open circuit the ideal current source. Okay, ideal current source. But what I will do, I will just stick on to the approach which is being used in Boylsted textbook, and in the later half I will propose my approach. All right. So what I will do, I will apply Thevenin's theorem. So on the input side, I'm going to create a short circuit. Okay, this is my ground, and this is where my Vi used to be. Okay, and then you will have your base terminal, across which you will find your base resistor Rp. Okay, and then you will have your input resistance Ri. Okay, that is later gets connected to the emitter terminal, and between emitter and ground, you are going to have the current source, okay, beta D into IB, okay, and you will have RE, okay. So what we will do is we will consider a pessimistic voltage source V across the output. So this is my pessimistic voltage source. Okay, which is meant for the calculation purpose, that's all. Okay, so let us assume that this pessimistic voltage source is circulating some current I, okay, some current I. Now at this node, what happens is that this current is going to divide into two parts, okay. Let's say I dash through RE, okay. Okay, sorry, this is your upward current direction, and beta D, okay. Now, since this is short circuiting this particular resistor, what will happen is this will vanish, okay, because this short circuit will remove the base resistor RB, okay. So due to which what will happen is you will be left with Ri here, okay. So I'm just shifting it here, and then the emitter terminal, okay, and then this resistor, okay. See, this emitter current we have simply replaced with beta D times IB. Strictly speaking, it should have been 1 plus beta D times IB, but for reference we have taken it as beta D times IB, okay. And this is your RE, okay, and this is your voltage source V, okay, which is connected just for the simplification purpose, okay. So this is I, and this is I dash, okay, and this current, you know, this current we can take it as IB because that's the base current, right? So apply KCL at node E, okay. Node E will give us IB, incoming current, plus the second incoming current beta D times IB, okay. Then you have, okay, this current, okay, this current which is I minus I dash, correct, because this current I enters at this node, okay, I mean it meets at this node and it is going to divide into two components, I dash component through RE and some component through this straight path, okay. And that current, you know, you can find using KCL, which is main current minus the branch current, so I minus I dash. So here let me directly write plus I minus I dash is equal to 0, okay. But expression for IB is already known, okay. Expression for IB is basically V divided by Ri, okay, and there's a negative sign, okay, because see, the voltage across beta D IB, okay, is 0, right? Voltage across ideal current source is 0. So whatever voltage, you know, that appears across Ri is nothing but this voltage V, okay. But remember that the current direction, you know, through Ri we have taken it in clockwise direction, but your pessimistic voltage source V is trying to circulate the current in the opposite direction, hence the negative sign is being placed, okay. And on the output side you can write I dash is equal to V divided by Re, right? I dash is nothing but voltage across Re divided by the resistance, okay. Now here the current is actually matching, okay, current is actually matching the source current sent by voltage source V, So you will find a positive sign over here. Okay, let's take this as 2. Let's take this as 1. So substitute 2 in 1. Okay, so when you substitute equation 2 in equation 1, you would get IB is equal to minus VI by RI plus, okay, what I will do, minus I will write, because I will write beta D into IB. IB again minus V by RI, right? So minus V by RI. That's the reason there is negative sign here. Then plus I, okay, and then minus because there is minus sign, V by RE, okay. Or you can, write I is equal to, okay, what you do is equal to 0. You take all voltage terms onto the right hand side. So you would get I is equal to V by RI plus beta D into V by RI plus V by RE, or you can take out the ratio, okay, V by I. Okay, before that, let me take out all voltage terms outside the bracket. So this is V1 divided by RI plus beta D divided by RI plus conductance, that is reciprocal of RE, or take out the ratio V by I. So voltage to current ratio, let's define it as output impedance Z0. So Z0 is basically reciprocal of all these. So that's 1 by RI plus beta D RI plus 1 by RE. Okay, so that's your Z0. Okay. Or because you are taking out the ratio, or you can directly write Z0 as, okay, Z0, or Z0 can be represented with the help of 3 resistors connected in parallel. Okay, that is something like this. RI, and this is your, again, reciprocal of this, right? So that is RI by beta D, and the reciprocal of this, that is RE. So this is V, and this is I, and this is your Z0. So you can write Z0 as RI parallel with RI by beta D parallel with RE. Okay, so that's your Z0. Okay. But remember one thing, this ratio RI by beta D, okay, this is small and this is large. Okay, so due to this, small and large values, what happens is that ratio RI by beta D is very small. So it's something like you are connecting a small resistance in parallel with the 2 other resistances, due to which your Z0 will be the least resistance among the lot, right? Amongst others. That's because RI by beta D is very small. So your Z0 is approximately equal to RI divided by beta D. RI divided by beta D. Okay, so this is your output impedance. So this shows that output impedance is very small, very small. Okay, so that's your analysis. Zi, Z0 we have found, and then we also found EAV and EAI. Okay, so the important characteristics of Darlington emitter follower is that current gain is very high, then voltage gain is unity with 0-degree phase shift, okay, and high input impedance and low output impedance. The applications are something like impedance matching, okay, just like your emitter follower, impedance matching. That's the first application. And the second application, it can be used as a buffer amplifier. Okay, buffer amplifier is nothing but isolating circuit, just like your transformer. Okay, and since beta D is very high, okay, it can be used as current amplifier. Current amplifier. If you want to increase the value of output current, Darlington emitter follower is the best circuit to use, simply because the overall current gain is theoretically the product of individual current gain. Okay, so these are the major applications of Darlington emitter follower. Okay, so in this analysis, what you have to look into is the output impedance. So output impedance analysis is slightly different. Okay, so this is it. Okay, so that's about your Darlington emitter follower analysis. So we are done with point number 1, point number 2. Now let us take the Miller capacitance. Okay, Miller capacitance. Very easy to understand, Miller capacitance. Okay, which is very important, Miller capacitance. Normally for 6 to 8 marks they will ask. Okay. The third topic. All right. Now, this Miller capacitance, I need to tell you the prerequisites, okay, to understand Miller capacitance effect. Okay. Any analog electronic device, okay, any analog electronic device suffers from something known as stray capacitance.
भैया मेरा नेटवर्क कितना 5.7 kb per second ऐसा आ रहा तेरा वो कितना था
उतारा खाली 150 तो आना कम से कम
Abdul Wasim. Okay, it's okay. By mistake, you must have done it. Okay. Stray capacitance. Now, this stray capacitance exists in the high frequency region. High frequency region. Okay. Now, if you, okay, let me keep it as simple as possible about this stray capacitance discussion, okay, because it is beyond our syllabus. That's the reason. Right. Now, this is our transistor symbol, right? It's a 3-terminal device. You have 3 terminals: base, collector, and emitter. Okay. And when we connect to our circuit for common emitter configuration, what we do is we ground the emitter terminal, right? Now, the base terminal as well as emitter terminal, okay, there will be some resistor Re, okay, don't worry about it. Now, what you have to understand is that the contacts, okay, provided at base terminal, emitter terminal, or to that matter, even at the collector terminal, is made up of metal, right? The metal contacts have been provided at the 3 terminals of the transistor. Now these metal contacts are provided so that an external circuit can be formed, right? But what happens is that during the transistor operation, okay, the base terminal, okay, will be at some voltage VB, all right, and the emitter terminal will be at some voltage VE, okay. So base terminal will be at some voltage VB and emitter terminal will be at some voltage VE. Okay. Now both base terminal and emitter terminal are made up of metals. So what I will do, I will try to show you the equivalent circuit. This is your base terminal and this is your emitter terminal. Now between base and emitter, what do you have? Between base and emitter, you have the medium as air. Are you following? Between base and emitter terminal, the medium is air. So between the two metal electrodes, you have air, and air is a dielectric medium, right? So air is an insulating medium. Air is an insulator. So indirectly, there exists a parallel plate capacitor or a simple capacitor because you have two metal contacts and these two metal contacts have been separated with air. Air is acting like an insulator. So there exists a capacitance effect between the terminals of the device. Okay. So there exists an inter-electrode capacitance. Since these two are electrodes, that's the reason this capacitance is called as inter-electrode capacitance. In other words, it is called as stray capacitance or parasitic capacitance. Parasite, right? Biological term, parasitic capacitance. Okay. So parasitic as in, to the naked eye, that capacitance doesn't, see. I mean, you will not be able to see using your eyes, but there exists, and its effect can be felt when we, carry out something known as frequency analysis. So that's the reason the name is given as parasitic capacitance. So this parasitic capacitance exists between base and emitter terminal. It also exists between collector and emitter terminal. Okay, and it also exists between base and collector terminal. So BC. Okay, and this is CDE. DE. So these inter-electrode capacitance for a common emitter configuration, okay, you can say there are three: base to emitter, collector to emitter, and collector to base. Okay, BC or CB doesn't matter. Okay, so this is called as the inter-electrode capacitance. Now the Miller effect capacitance is nothing but the capacitance which is the largest amongst the three. Okay, so that is this capacitance, base to collector capacitance, or capacitance found between the input terminal and the output terminal. Okay, see, this is your input capacitance, right? Base to emitter. Okay, and collector to emitter is kind of output capacitance. Okay, but collector to base capacitance is the capacitance measured from the input base terminal and the output collector terminal, and that capacitance is the largest capacitance in comparison with the other two. So this effect is observed by a telecom engineer called Miller. Hence the name is given as Miller effect capacitance. Okay, Miller effect capacitance. Now, the effect of this Miller capacitance is that it modifies overall input and output impedances. The effect of Miller capacitance is something like it modifies input and output impedances, due to which gain gets, or we can say voltage gain gets modified, and hence performance is disturbed. Okay, so this is a very short discussion about the stray capacitance. Okay, now let us look into the Miller capacitance. Okay, but did you understand, or at least did you get the feel of it, how exactly this parasitic capacitance comes into picture? Now, the effect of parasitic capacitance is negligible at low frequency. Okay, that's because Xc is inversely proportional to F. So when frequency is low, Xc is very large. So your parasitic capacitance is open circuit at low frequencies. So your parasitic capacitances can be regarded as an open circuit element, okay, at low frequency. But at high frequency, you cannot treat them as an open circuit element. Okay, that's because at high frequency, okay, at high frequency, the reactance is very low. Okay, so at high frequency, parasitic capacitance behaves like short circuit elements, and therefore it creates, okay, it creates virtual shorts in transistor circuits. Therefore the gain gets reduced. Okay, this is very important for Viva as well as in the competitive examination. Okay, so they may ask what is the major cause for dip in voltage gain in the high frequency region. So dip in voltage gain in the high frequency region is attributed to the presence of parasitic capacitance, and at higher frequency the parasitic capacitance is very, very small, so it can be treated as short circuit element. So there exists multiple short circuits across the transistor terminals. Okay, there will be a short circuit between base and collector and emitter, and base and emitter. So due to this virtual short, the voltage gain gets reduced. Okay, voltage gain gets reduced, and the overall gain will be much lower in comparison with the expected value. So this is the effect of parasitic capacitance. Okay, all right. So derivation, I don't think so I'll be able to do it. Let me take the derivation tomorrow and the remaining portion as well. All right. So that's it for today. So did you understand the effect of parasitic capacitance? Can anyone just let me know?
Yes, sir.
Okay. So very important, if at all, if you aspire to be a VLSI engineer or a design engineer. Okay, so this parasitic capacitance is one of the major cause for the IC manufacturing. Okay, so you cannot, it's very difficult to get the layout done in quantum level. That's because of at quantum level, there will be a lot of parasitic capacitances. Okay, a lot of parasitic capacitances. That's the reason, this quantum transistor or whatever quantum solid state physics is kind of exploratory in nature. Okay, so that's the next breakthrough, you can say. If you are able to handle these parasitic capacitances, you will be able to get into quantum computing systems. All right, fine. So I will float a quiz based on this. So take a day of time to complete that quiz. Okay, fine. If you haven't given the attendance, please give the attendance. Okay, others can leave. Thank you.